In this video, we'll talk about the basic file system organization, the rule of the VFS. We're going to talk about what file systems are available in Linux and which ones can be used on your actual system. Why generating file systems represent significant advances. We're going to discuss the use of special file systems in Linux. Okay, let's begin. File system basics. Application programs read and write files rather than dealing with the physical locations on the actual hardware on which files are stored. File systems create a usable format on a physical partition. Files and their names are an abstraction camouflaging the physical I/O layer, directly writing to disk from the command line. Ignoring the file system layer is very dangerous and is usually only done by low-level operating system software and not by user applications. An exception is some very high-end software such as enterprise databases that do such CMD access to skip file system-related latency. A Unix-like file system uses a tree hierarchy. Directories contain files and/or other directories. Every path or node is under the root direction. Multiple file systems may be, and usually are, merged together into a single tree structure. Linux uses a virtual file system layer, VFS, to communicate with the file system software. Local file systems generally reside within a disk partition, which can be a physical partition on a disk, or a logical partition controlled by Logical Volume Manager (LVM) file systems. File systems can also be of a network nature, and their true physical embodiment completely hidden to the local system across the network. Inodes. An inode is a data structure on disk that describes and stores file attributes, including its location. Every file which is contained in a Linux file system is associated with its own inode. All data about a file is contained within its inode. The inode is used by the operating system to keep track of properties such as name, location, file attributes, permissions, ownership, etc. Access times and other items. Because of this, all I/O activity concerning a file usually also involves the file inode. Inodes describe and store information about a file, including permissions, user and group ownership, size, timestamps, nanosecond, right? Last access time, last modification time, change time. Hard and soft links. A directory file is a particular type of a file that is used to associate file names and inodes. There are two ways to associate or link a file name with an inode. Hard links point to an inode, or hard linked files have to be on the same file system. Changing the content of a hard linked file in one place may not change it in other places. Soft or symbolic links point to a file name which has an associated inode. Soft linked files may be on different file systems. If the target does not yet exist or is not yet mounting, it can be downlink. Each association of a direction file contents and an inode is known as a link. Additional links can be created using LN. Because it is possible and quite common for two or more directory entries to point to the same inode, hard links, a file can be known by multiple names, each of which has its own place in the directory structure. However, it can have only one inode no matter which name is being used. When a process refers to a path name, a kernel searches directories to find the corresponding inode number. After the name has been converted to an inode number, the inode is loaded into memory and is used by subsequent requests. Let's see some example. cd temp touch file, the soft link -s file soft and file hard os dash file virtual file systems VFS. Linux implements a virtual file system VFS, as do all modern operating systems. When an application needs to access a file, it interacts with the VFS abstraction layer, which then translates all the I/O system calls, reading, writing, etc., into a specific code relevant to the particular actual file system. Thus, neither the specific actual file system or physical media and the hardware on which it resides need be considered by applications. Furthermore, network file systems such as NFS can be handled transparently. This permits Linux to work with more file system varieties than any other operating system. This democratic attribute has been a large factor in its success. Most file systems have a full read and a write access, while a few have only read access and perhaps experimental write access. Some file system types, especially non-Unix based ones, may require more manipulation in order to be represented in a VFS. Variants such as VFAT do not have distinct read, write, execute permissions for the owner group would field, right? The VFS has to make an assumption about how to specify distinct permissions for the three types of user, and such behavior can be influenced by mounting operations. There are non-kernel file system implementations, such as the read-write NTFS-3G, which are reliable but have weaker performance than in kernel file systems. Readable file systems. Linux works with more file system varieties than any other operating system. This democratic flexibility has been a large factor in its success. Most file systems have a full read-write access, while a few have a read-only access. Commonly used file systems include ext4 XFS, Butterfly RFS, Squash FS, NFS, and VFAT. A list of currently supported file systems is at this location. Proc file systems. File system varieties. Linux supports many file system varieties, most with full read and write access, including ext4, the Linux native file system, and earlier ext2 and ext3. XFS, a high-performance file system originally created by SGI. JFS, a high-performance file system originally created by IBM. Windows natives, FAT12, 1632, VFAT, NTFS. Pseudo file systems resident only in memory, including proc, sysfs, devfs, debugfs. Network file systems such as NFS, CODA, AFS, etc. You can see a list of the file system types currently registered and understood by the currently running Linux kernel by doing cat proc file systems. The ones with the no dev are special file systems which do not reside on storage. Additional file systems may have their code loaded as a module only when the system tries to access a partition that uses them. Journaling file systems. Journaling file systems recover from system crashes or ungraceful shutdowns with little or no corruption, and do so very rapidly. Well, this comes at the price of having some more operations to do. Additional enhancements can more than offset the price. In a journaling file system, operations are grouped into transactions. A transaction must be completed without error automatically. Otherwise, the file system is not changed. A log file is maintained of transactions. When an error occurs, usually only the last transaction needs to be examined. For journaling file systems, ext3 was an extension of the earlier non-journaling ext2 file system. ext4 is a vastly enhanced outgrowth of ext3. Features include extends 48-bit block numbers and up to 16 terabyte size. Most Linux distributions have used the ext4 as the default file system for quite a few years. Reserves was the first general implementation using in Linux, but lost its leadership and further development was abandoned. JFS was originally a product of IBM and was reported from IBM's AIX operating system. XFS was originally a product of SGI and was ported from SGI's IX operating system. RHEL7 adopted XFS as its default file system. Butterfly RFS is the newest of the journaling file system and is still under rapid development. It is the default for SUSE and OpenSUSE systems. Special file systems. Linux widely employs the use of special file systems for certain tasks. These are particularly useful for accessing various kernel data structures and tuning kernel behavior or for implementing particular functions. Note that some of these special file systems have mount points such as proc at proc or sys at sys, and others do not. Examples of special file systems that have a no mount point include sockfs or pipefs. This means user applications don't interact with them, but the kernel uses them, taking advantage of VFS layers in the code. These special file systems are really not true file systems. They are kernel facilities or subsystems that find the file system structural abstraction to be a useful way to recognize data on the functionality. I'm going to explain all those special file systems here. Let's start with rootfs. There's no mount point. There's a during kernel load, provides an empty root directory. Huge TLBFS, it's mounted anywhere. It provides extended page access 204 MB on x86. bdev, it's no mount point, used for block devices. Proc, mounted to proc folder. It's a pseudo file system, access to many kernel structures in a subsystem. sockfs, there's no mount point, used by BSD sockets. TMPFS, mounted anywhere. RAM disk with swapping resizing. SHM, no mount point, used by system of VIPC shared memory. Pipefs, no mount point, used for pipes. binfmt mist, mounted anywhere, used by various executable formats. debpts, mounted debpts, used by Unix 98 pseudo terminals. USB-FS, mounted to proc bus USB, used by USB subsystem for dynamic devices. sysfs, mounted to sys, used as a device tree. debugfs, mounted to sys kernel debug, used for simple debugging file access. Okay, this is the end of this video. Thank you for watching. I'll see you in the next one. Bye for now.